So it's a great pleasure to introduce David Harvey, who is an associate professor up at UNSW Sydney. He was a winner of the Ostermess Medal back in 2019, and for a while, photographic evidence on his website bears this out. He had a beard just like mine, but I've been able to outbeard him over these past few months. I'm looking forward to his talk. His talks are always known for clarity and erudition, so thank you very much, David.
Thanks, Tim. And thank you very much to Sasha and Dimitri for organizing this conference. Right, so I'm going to be speaking about some work on integer factorization that I've been doing over the last year or so. And quite a lot of this is joint work with Marcus Hittmeir, who I've never actually met. We've collaborated entirely by email, actually. Okay, so this is the problem we're interested in, is given a large integer n, we want to find its prime factors. So here's an example of such a problem. This is the RSA 250 challenge number. There's a 250 decimal digit number. So RSA is a crypto system, and there's a corporation called, I think, the RSA Corporation, and they proposed this challenge quite a few years ago. I think it was maybe early 90s. They basically published a bunch of large composite numbers of increasing size, which they said were made up of two prime factors. They had generated the primes, multiplied the numbers together, and then thrown away the prime factors. And the challenge is to compute the factors, and it was supposed to be a benchmark for what is the state of factoring at the time. And I think they offered cash prizes for a while. I don't think the cash prizes are available anymore. Anyway, this was one of their numbers that you had to factor. Now, there's the well-known trial division algorithm is the simplest factoring algorithm. You just try dividing by all the numbers up to n. But then, of course, even my kids know that you don't have to go all the way up to n. You only have to go up to the square root of n. So that's very helpful for this RSA challenge, because for the number I showed you on the previous slide, you only have about 10 to the 125 candidates. I suppose a little less if you only have to divide by the prime ones. But you can see that's going to take you a very long time. So this is an example of an exponential time factoring algorithm. The complexity is roughly n to the 1/2. And the reason I have the little epsilon there is just because dividing by an integer n is not a constant time operation. It depends on the size of the number you're dividing by. So in general, exponential time means n to the c. And we call it exponential because the size of the input is proportional to log n. It's the number of digits you need to write down n. So on the other hand, the holy grail is to find a factoring algorithm which runs in polynomial time. So that would mean that the running time is log n to some constant. So if you have a quantum computer available, then you can use Shor's algorithm to do this. It can factor any integer n in roughly time log n squared. Now, I'm not an expert on quantum algorithms, and a year or two ago, I went and did some reading. I thought I should learn about this stuff, and read a bit about quantum mechanics and quantum algorithms and Deutsch's algorithm and all this crazy stuff, and tried to understand Shor's algorithm and got very confused by, Schrodinger and Heisenberg and all this stuff. And finally, I think I came to understand Shor's algorithm, and I want to explain it to you. It runs roughly like this. As far as I can tell, what you do is you take an animal, usually a cat in most descriptions, but I suppose any animal would work, and you put it in a box with some radioactive substance. This is quite dangerous. You've got to be very careful. It's very cruel to the animal. And what you do is you write down the integer n on a piece of paper and you shove it in the box and you close the lid. And then you wait a while. I'm not sure exactly how long you have to wait. This is never made clear in these descriptions. But then you open up the box. And the question is, what do you see? What has happened to the cat? Now, if the cat is alive, then n is prime. And this is great because you've also got a polynomial time primality test, which is really nice. But if the cat dies, then that's fantastic because you've got the factors of n. Okay, so this is a very cruel algorithm. I don't advocate running this algorithm, and I can't run it anyway because I don't have any pets, any cats or anything else. I suppose I have children, but let's not go there. But I don't want to talk about these algorithms anymore today. I'm talking about only classical algorithms for the rest of this talk, so no quantum algorithms. So algorithms designed for a classical computer. So the RSA challenge number I showed you has been factored. That's the largest one that's been factored. That was done just last year by a bunch of computational number theory sort of people. So here are the two factors, P and Q. They're pretty forbiddingly large prime numbers. No, it's actually quite hard to even check a number that big is prime. And you can multiply together numbers like this very quickly if you have a computer. I wouldn't recommend doing it by hand, but you can easily check that you get n. And actually, I did this. I actually did this last week just to make sure they weren't playing tricks. So how did they do this factorization? They used an algorithm called the number field sieve, which goes back to the early 1990s. And that computation was not a trivial computation. It took about 2,500 years of CPU time, which is certainly not a trivial amount of computation time. I mean, it's not, there have been computations bigger than this have been done for sure. But in number theory, it's actually pretty big. So this is the fastest known method we have for factoring big numbers. And here is the conjectured running time. So what is going on here? We've got this constant 64/9 stuff here. The important part is this log n to the 1/3, exp of log n to the 1/3. So this is faster than any exponential time algorithm, right? Exponential would be exp of some constant times log n, and this is log n to the 1/3. So it's a lot better than that, but it is much worse than polynomial time. Polynomial time would be exp of a constant times log n. Now this function log n to the 1/3 is much closer to log n than log n. So this is definitely much closer to exponential time than polynomial time. So we're still a very, very long way away from polynomial time classical factoring algorithm. Okay, now the problem with this algorithm is that the running time bound depends on a lot of heuristics. Right? We're not remotely close to being able to prove a running time bound like that. So it works in practice, but as mathematicians, it's a big problem because what we really want is a rigorously proved complexity bound. Now, if you don't know who the guy in the picture is, or don't know what movie this is from, then obviously you're too young to be at this conference. Shouldn't be allowed here. If I remember correctly, this movie came out, I think, about the same time as the number field sieve, actually. It was early 90s. Okay, if we want to restrict to rigorous algorithms, then the fastest known rigorous factoring algorithm is due to Lenstra and Pomerantz, and this is a version of the class group relations method. Now this is a randomized algorithm. So the way I think about this kind of algorithm is it actually needs some extra input, not just the number you want to factor, but it also needs a sequence of coin flips as input. And they have to be truly random. If they're not truly random, then their proof doesn't work. So what you get is an expected running time bound. So the running time is actually a random variable, and it could take a very long time if you're very unlucky. But what they prove is the expected running time bound is given by this sub-exponential function. So it's not quite as good as log n cube root. It's just the square root, but this is still sub-exponential. And I should emphasize the randomness here is not to do with the choice of n. They're not saying that, if you choose a random n and try to factor it, then this is how long it takes. This works for every n. It's just the running time is a random variable. Okay, but again, this is not good enough. For this talk, I only want to stick to deterministic algorithms, right? I don't want to have to get lucky to factor my number n. I want the algorithm to just work in a rigorous, deterministic way. So for the rest of the talk, those are the restrictions I'm operating under. Now here is the problem. This is very embarrassing, but every algorithm we know, which is deterministic and which we can prove a running time bound, actually runs in exponential time. And the only question is, what is the exponent? So here is the best current result, and this is a preprint by myself and Marcus Hittmeir just this year, is that we can factor an integer into primes in about n to the 1/5 time. And if you're a little bit more careful, you can work out the power of log n and even a power of log n that shows up in this complexity bound. So when you're being this precise about the complexity, you have to say what your computational model is. And so we're working here with a pretty standard model in computer science, which is the number of steps on a deterministic multi-tape Turing machine. So this is a Turing machine that has a fixed finite number of tapes and a fixed finite alphabet and a fixed finite number of states in the processing machine, and you write the input on one tape, and it's supposed to write the factors to another tape at the end of the execution of the algorithm. And then this is the number of steps. So really sort of number of bit operations, if you like. And I should mention, since we are in the Richard Brent celebration mode, that this paper was dedicated to Richard for his recent birthday. So thanks very much, Richard, for all the fantastic work you've done so far, and all the fantastic work that is still to come.
Thanks, David.
Just briefly about the history of this problem. So what has been proved in the past? Now, this is not a complete list, but I've tried to put down what I think are the most important sort of waypoints on this sort of rigorous deterministic under these restrictions. So the first algorithm I mentioned is an algorithm of Shanks from 1971, which achieved n to the 1/4 using class groups of quadratic fields. So you basically look at the quadratic field associated to n, and I think you have to find an element in the class group of order 2, and that enables you to factor n. Now, I have to say I'm a little bit nervous about this Shanks algorithm, because I don't think the original presentation was intended to be rigorous. When you look at the paper, it's sort of written in this very informal, casual, conference-style way, and he's really interested more in practical computation than in proving things. And I haven't really convinced myself that the argument is rigorous. I asked Carl Pomerantz about this, and he seemed to think it was. So I'm going to defer to Carl on this, but I'm still a bit confused, and hopefully someone can explain this to me one day, or I need to just go and read the right source about this question. Anyway, let's just work with it for the moment for the purpose of this talk. Okay, the second one I mentioned is an algorithm a few years later by Lehmann. This is a very elementary algorithm which got n to the 1/3 complexity, and there's been a lot of algorithms since that get n to the 1/3. I think this was the first one that I'm really comfortable saying, yes, I believe this algorithm works. Then there's a pair of algorithms due to Pollard and Strassen around the same time. They got n to the 1/4 using fast polynomial arithmetic, so fast Fourier transforms and that sort of technique. These algorithms are very similar, but they're not exactly the same. But they're so similar that you often hear people talking about the Pollard-Strassen approach, and I've certainly been guilty of that. But now I've started to think of them as being a bit different, and maybe I'll be able to explain it, why I feel this way a bit later in this talk. The new stuff is much more closely related to Pollard's algorithm than Strassen's algorithm. And I'll be talking a bit about both Lehmann's and Pollard's algorithm in the rest of this talk a bit later on. But finally, I'll mention another algorithm of Coppersmith in the mid-90s, another n to the 1/4 algorithm, which I think of as a generalization of Lehmann's approach. It's kind of like an optimization of Lehmann in a way. But he depends on fast lattice reduction algorithms like LLL. But the point I'm trying to make here with this list is that you can see on this list that there's something like 3 or maybe 4 or maybe 2 algorithms, depending on how you count them, quite different algorithms using very different ideas, which achieved this n to the 1/4. So it really felt like a very solid barrier. And all these algorithms were sort of discovered, most of them in the 70s, and Coppersmiths not, still a long time ago. So it was very surprising when last year, so this was after COVID hit, in about June last year, Marcus Hittmeir posted this preprint. He could have chosen a better title. I don't think the title was very punchy. I didn't realize what it was about. But he actually got it down to 2/9. He got the 1/4 down to 2/9, which is really amazing. And he's using a combination of ideas from these previous papers, but put together in a very clever way. And so, this was, I found this really amazing. And when I found out about this paper, I sat down and studied it very carefully. And then I realized he had missed a trick. And I was able to simplify his algorithm and get the exponent down a bit further, and got it down to 1/5. And that's where it sits at the moment. As you saw on the previous slide, that's the best result we know at the moment. So after this, Marcus and I got chatting, and we worked out a further improvement, shaving off another very small factor of power of log n. And in fact, we're now currently collaborating on another paper where we hope to improve the factor of log n just a little bit more. So the n to the 1/5 doesn't seem to be budging, but we can still do a little bit more with those smaller, with those powers of log n and log n. So what I want to do in the rest of this talk is basically explain how this n to the 1/5 algorithm works. And the way I'm going to do it is I'm first going to explain a version of Pollard's algorithm and a version of Lehmann's algorithm, because they're really the two inputs. If you basically take those algorithms and you fiddle with the parameters and you combine them in the right way, then you can recover this n to the 1/5 algorithm. So once I've explained those two algorithms, Pollard and Lehmann, which are quite different, then it will be very quick to put them together and show you how the n to the 1/5 works. You just have to be thinking about these predecessors in the right way. That's what I want to try and explain. Okay, so I'll start with Pollard's algorithm. And to simplify things, I'm gonna make a bit of a simplifying assumption. I'm going to assume that we know some element alpha. So this is an element of the multiplicative group of integers mod n. So n is the number we're trying to factor. So I'm going to assume we know some alpha, which has large multiplicative order. Now, normally, the way you could find such an alpha is you just pick a random alpha and you just try to compute its order, right? You just start taking powers of alpha, and you know, you can use there are tricks you can use to speed this up. You know, baby step, giant step, this kind of thing. So it's usually easy to find it, but if you're working deterministically and rigorously, then it's a little more intricate. And one thing I want to stress is there isn't always such an alpha. So you can see in this box here, I've written down a very small example. Here is an n, which is a product of 3 factors. And I've chosen these factors so that if these primes p, so that p minus 1 has this factor of 36. And what this forces, it means that there aren't any elements in Z mod nz that have order at least square root of n. They all have to have order at most 36. So it's kind of a stupid example. So you can't always find such an alpha. But what you can do, and I don't have time to go into the details of this, is that there is a deterministic algorithm which will either come up with such an alpha of large order, or it will find out enough about n that you'll be able to factor n using a different method. And this is quite an interesting story, which unfortunately I don't have time to go into. Basically, the idea is you sort of just try various alpha, and if all of them have small order, then you'll be able to discover this quickly. And the fact they all have small order is going to constrain n to have properties a bit like this n here. Okay, and you can use that information to, it's giving you extra information about the possible prime factors. So I don't want to go into that. Let's just assume we have this alpha of large order. Okay, so what does Pollard do? Well, it all hinges on Fermat's little theorem. So he says, suppose we have a prime factor p, and without loss of generality, we can assume it's less than the square root of n. So then we have Fermat's little theorem tells us that alpha to the p minus 1 is 1 mod p. Now this looks a little bit like a discrete logarithm problem, right? We've got this alpha, and we know it's equal to 1, and we're trying to solve for p minus 1. Now the problem is that we don't know the modulus. The modulus is also unknown, but that's fine. We'll be able to work around that. So we're going to try and solve for this p minus 1 using an algorithm design technique, which is often called baby step, giant step. I think, in fact, it might have been invented by Shanks in that earlier paper that I mentioned. Okay, so here is a picture of what's going on. So this diagram here is supposed to illustrate how you can think about this algorithm. So it's supposed to show the powers of alpha. So I've got on the left, I've got 1, alpha, alpha squared, etc. And I write down all the powers of alpha up to alpha to the d. What is d? Well, d is about the 4th root of n. Okay, so it's roughly the square root of the square root of n. So this diagram goes all the way up to d squared, alpha to the d squared, which is just a little bit beyond n to the 1/2. Here it is. And so you should think of this diagram as being cut up into blocks of size d. Okay, so there are these d blocks of size d, and these are the powers of alpha. And what I know is I've got alpha to the p minus 1 is somewhere in the middle here. I don't know where it is, but it certainly happens before I get to n to the 1/2. And I know that this alpha to the p minus 1 is 1 modulo p. Okay, so this is supposed to be alpha to the p minus 1 right here. And what I'm going to do is I'm going to split up p minus 1 in this form, id minus j, where I and j are both roughly smaller than d. So what I'm really doing is I'm saying I is telling me which block p minus 1 is in, and then j is telling me how far through that block it is. Okay, so it's almost like writing p minus 1 in base d. I've got the low digit is j and the high digit is I, except that I've messed around with the signs a little bit. Okay, so I hope this picture is clear. So what happens with Fermat's little theorem is we have alpha to the p minus 1 is 1 mod p, but then I can move the j onto the other side of the equation. So I get this identity here. Alpha to the id is congruent to alpha to the j mod p. And now the point is that this is a collision modulo p between two sets of elements of integers mod n. So on the one hand, I have these baby steps, right? They're the small steps, the powers of alpha. There's d of them, 1 up to alpha to the d minus 1. That's the right-hand side here. And on the left-hand side, I have the giant steps. These are the powers of alpha to the d. And what I'm telling you is there's only d elements here, and there's only d elements on each side, but one of the giant steps has to be congruent to one of the baby steps modulo p. That's what Fermat's little theorem is giving us. Okay, so what do I do with this collision? Well, Pollard's idea is to use some polynomial arithmetic to try and track down this collision. So what he's going to do is he's going to write down this polynomial f of x, which is a product built out of the baby steps. Okay, so if you like, it's a polynomial sort of whose roots are given by these baby steps. And you notice the coefficients here are taken modulo n. Everything you're working modulo n here. So you take this polynomial, and then we're going to evaluate it at the giant steps. So we've got a polynomial of degree d, and we evaluate it at d points, and we get some values in z mod nz. Now the key thing is, and to make this algorithm work, you have to know some facts about fast operations on polynomials. You can do this in essentially linear time in d. This is not obvious. If you just multiply out the polynomials and evaluate them in a naive way, you do not get something linear in d. You'll get something quadratic in d. You have to use faster methods, such as fast Fourier transforms. You don't quite need fast Fourier transforms to achieve that, but that's how they tend to be done these days. Now, once you've done that, and notice, by the way, this quasi-linear in d is basically linear in n to the 1/4. So that's where the n to the 1/4 complexity is coming from. Now, what does the collision do? Well, if you look at this collision, alpha to the id congruent to alpha to the j, what that's telling you is if you look at f of alpha to the id, it's going to have one of these factors divisible by p. At least one of these factors will be divisible by p, p being the unknown factor you're searching for. So what that means is if you take the GCD of all these values with n, then you're guaranteed at least one of them is not going to be 1. You're going to have a non-trivial GCD. I have to be a bit careful. When I say non-trivial, I just mean not equal to 1. Could be equal to n. That's unfortunate if that happens, but it's definitely not equal to 1. Okay, so what we do is once we've computed those values of f at the giant steps, we compute the GCD of all of those guys with n, and we know that one of them is not going to be 1. So as soon as we see that, we stop. And then we look at that GCD, and if it's not equal to n, then we win. We found a non-trivial factor. May or may not be p. I don't really care. I mean, as long as I found a non-trivial factor, then I've made progress. Now, unfortunately, it could happen that it could be n, right? In other words, that this value is actually 0 mod n. Now, if that happens, we're still okay, because what we can do is we know that it's a product of a bunch of these d factors. And here is where we have to use this hypothesis on the order. We know the order is large, and this guarantees that none of these factors are actually themselves divisible by n, right? Which means there has to be an interesting factor in there somewhere. So then what we do is we compute the GCD of each of these guys with n. And again, there's only d of them, so we have time to do that. And we're guaranteed to find a non-trivial factor. So sometimes this procedure is it's called backtracking sometimes. So that's how the algorithm works. I want to give you a quick numerical example, just a baby example, so you can see how it works. So here's the number n I'm trying to factor. It's a very large number. Probably still bigger than any numbers that quantum computers have factored so far, but anyway. So d here is 6, that's about the 4th root of n. And I'm going to take alpha equals 7, that's my element of large order. I can't remember why I chose 7. Maybe I just looked for an element of large order, and that's what I came up with. So here are the baby steps, powers of 7, modulo n. So they're easy to calculate. And then we compute the polynomial f. That's a product of those terms built out of those baby steps. And here it is. It's just some polynomial modulo n of degree 6. Then we compute the giant steps. These are the powers of alpha to the 6. And then we evaluate the polynomial f at those 6 points. And we get these 6 values. And now we compute the GCD of each of these values with n. And when we get to this third one here, 646, we find it has a GCD of 17. So we found a factor of n, 17, and then we can easily divide to find the other factor, 71. And so where did this 17 come from? It came from a collision, in this case, between this element here, 576, and this element here, 49. They happen to agree modulo p. So basically, Pollard's argument proves that there has to be at least one collision. Okay, so that's Pollard's algorithm. So I want you to file that away now, and we're going to talk about Lehmann's algorithm, which is a completely different idea. So before I start on Lehmann's algorithm, I just want to mention that I sort of realized as I was writing this talk that the way I was planning to present Lehmann's algorithm doesn't look at all the way that Lehmann's algorithm is presented. I've seen, in his original paper or in the book by Crandall and Pomerantz, it looks quite different. And I think what's happened is that I've gotten so used to thinking about Coppersmiths' algorithm that I started thinking of Lehmann's algorithm as being organized the way that Coppersmiths' algorithm is organized, which is not really, I don't think is really how Lehmann was thinking of it, but they're very, very close. And so maybe it won't be recognizable, but anyway, I hope you'll allow me this indulgence, because this is the way I think about this algorithm now. Okay, so here's what we're going to do. Suppose we've made an initial guess for what our factor is, and I'm going to call this guess P0. Now, P0 is supposed to be close to P, whatever that means. And so we're searching for a divisor near P0. So I want to look at this function, f of x, which looks like the following. It's an over x plus bx. So here a and b are supposed to be small integers. And I'll discuss in a moment what properties we want a and b to have. But the first thing I want to point out about this function is that if x is a prime dividing n, in fact, if x is any divisor of n, then f of x is an integer. This takes integer values when we have a factor of n. So that's what the game is going to be. We're going to look for values of x for which this function is an integer. Okay, so what does Lehmann want to do? What he wants to do is he wants to choose the a and b very carefully, so that this function is pretty much a constant function near P0 when x is near P0 on as large an interval as possible. Okay, so the way I think about this is, think about the function bx, right? Bx is a function with a slope of slope b. And in this function, an over x is a decreasing function of slope, whatever it is from calculus, something like minus n over x squared. And you're taking some weighted sum, and you want to sort of calculate the weights so that the function is close to being horizontal near P0. Okay, so you're basically doing some calculus. So that's how you want to choose your a and b. Okay, suppose we've done this. Suppose we've found our a and b, and we've got this situation now. And now we want to find p in this interval. So what we do is we look at f of P0. That's this quantity in the brackets here, f of P0. That's just some real number. And we look at integers near that number. And we know that if p is a divisor of n, then, if x is a divisor of n, then f of x is going to have to be an integer close to this number. So it's going to have to be one of these integers that we're looking at. So then what we do is we just check each of the integers nearby to see if they're of this form, to see if they're of the form an over x plus bx. And this is very easy to do for any particular integer because you're really just solving a quadratic equation in x. So it comes down to just checking whether a certain discriminant is a square. So this can be done very quickly. The issue is to come up with these candidates. Once you've got a candidate, it's easy to check. Okay, so that's the strategy. Now the question is, how do we choose A and B? So let me explain how to do this. So there's a little bit of algebraic manipulation involved here. So here's my function, an over x plus bx, and I'm going to take an x which is close to p0. It's going to be p0 times 1 plus delta, and delta here is just some small number. So then you do a bit of calculus and you expand things out, and you get this expression here. And you can see here is the f of p0. That's just the first term in the Taylor expansion. This is the linear term. An over p0 minus bp0 is the coefficient. And then I've just lumped everything else together in a quadratic term. So what we have to do is we want to make these two error terms to be of the last two terms here to be O of 1. And so this is the issue. We need to choose A and B and the bound on delta so that these inequalities hold. Now, if you stare at this for a moment, you'll see what's going on. This expression here on the left in the big brackets, an over p0 minus bp0, if I want that to be small, that's just saying I want a over b to be a good rational approximation for p0 squared over n, right? And that matches what I was saying before about this picture, right? We just want to choose the slopes so they cancel out, okay? And then the other term, what we need is an over p0 delta squared to be small, and that basically comes down to saying we want a to be not too big. In other words, we want a rational approximation of low height. Now, we have several experts in the audience on Diophantine approximation. I'm not an expert, but I do know the most basic results in this area, and this is really all we need here. So this is a well-known theorem about approximating arbitrary real numbers by rational numbers. If we want to approximate some zeta by a rational number, and we want the denominator less than some capital B, then we can do it with this error term, 1 over little b times big B. And one way you can do this is you can compute the continued fraction of zeta, and then look at the convergence in the continued fraction approximation, and just take the last convergent where the denominator B is less than or equal to the bound you're interested in. And this will be the one you want. This will be the A over B that you want. So I'm going to apply this lemma with this zeta, p0 squared over n, and this bound turns out to be the right bound that you need. And I won't go through all the details, but here's what you end up with. You end up being able to get this O of 1 error term. For this kind of interval, you need an interval around p0 where the width is p0 over the cube root of n. That turns out to be what falls out of this optimization problem. Okay, so what's happened is on this interval of quite reasonable size. I mean, this is a fairly large interval, right? So in the typical case where you're looking for prime divisors around the square root of n, this interval is about n to the 1/6 wide. So it's a pretty wide interval. So it's saying whenever you're in this interval, f of x is very well approximated by f of p0, right? The error is only O of 1. Okay, now to turn this into an algorithm, we can't just do this for a single p0. What we need to do is cover all the possible, everywhere from 1 up to square root of n. We need to cover that whole interval by intervals of this sort for a bunch of values of p0. It's like we take lots of different guesses, and for each one we try to see if we run this procedure to see if p is in that interval. And the number of intervals is about n to the 1/3. Okay, there's an extra annoying log n factor. That's just coming from the fact that this interval, the width depends on p0, right? There is a p0 here. The intervals get shorter as your target gets smaller. So that gives you this extra log n factor. So basically, that's the number of search intervals, and you can do each search interval in essentially polynomial time. So the running time ends up being about n to the 1/3. Now, I know that's all a bit of a mouthful, so I'm just going to show you a numerical example. And this is show you this is actually a very, very cool algorithm. So here's a number I'm going to factor. What is that, 40 digits or something? And let's suppose we've guessed this factor. There's a factor near this P0. Okay, here's my P0. And I've chosen P0. The last 6 digits are 0. That's just to emphasize the fact that I don't really know the last 6 digits of P. I'm assuming I know roughly the first 2/3 of P, but not the bottom third of P. And Lehmann's algorithm is going to fill in the missing digits. It's going to sort of home in on the exact P in this interval. So the recipe is we calculate P0 squared over n. Here it is, big ugly rational number. And then we compute the continued fraction of that number. And we stop, we compute the convergence and we stop when we hit this threshold. And so here's what we get. We get A over B is this crazy rational number here. And the A and B should both be of size, I think it's n to the 1/6. Okay, so roughly 1/3 of the size of P0. Okay, and you see they're roughly 6 digits long. Okay, so we've got our A over B. And then all the theory I've just been going through tells us that AN over P plus BP, this is f of P, it should be an integer very close to this integer here. Okay, so, sorry, to this real number here. This is just some real number. Now, what we have to do is check some nearby integers. And the obvious one to try is the ceiling, which actually turns out to be the right one. So we take C to be the ceiling of that number. And then we have to solve this equation for P. Okay, and it turns out it does have a solution. Here it is, that's P. So it's immediately filled in the last 6 digits. And then we get the other factor n over P. So I want to stress that I didn't have to check like a million things, right? If I was doing this using trial division, I would have to check a million possible numbers in this interval to check that none of them divided n. But Lehmann was instantly able to home in on the right last 6 digits. And that's why you get the saving. That's why you go down from n to the half down to n to the 1/3. Okay, I just want to briefly mention how this generalizes to give you Coppersmiths algorithm, because once you've thought of Lehmann's algorithm this way, it's very easy to see how to do Coppersmith. So Coppersmith does the same thing with higher degree polynomials. So here's an example where I've bumped the degree from 1 to 2. So now this function, I've got an n squared over x squared. Well, that's an integer if x divides n. Okay, so f of p is going to be an integer. And then the issue is to choose a, b, c, and d so that this function is close to a constant near x equals p0. And what happens, instead of doing continued fractions, you have to search for a certain short vector in a certain lattice. And you can do that using LLL. And then what happens is as you increase the degree of the polynomial, the search interval width gets bigger. So instead of being 1/6, it increases to n to the 1/4. So you have to search fewer intervals. You have to do a bit more work in the lattice reduction, but lattice reduction is really fast. That's polynomial time, and so you end up winning. And you get a complexity of n to the 1/4 in the limit. Okay. So I've now explained Pollard's n to the 1/4 algorithm and Lehmann's n to the 1/3 algorithm. And now I want to show you how you combine these ideas to get to n to the 1/5. Okay. So here again is what we proved for Lehmann's algorithm. We approximated f of x by f of p0 plus o of 1 in this search interval. Now, the question is, what happens if you just make the search intervals wider? Right? What happens if we try wider search intervals? So what happens is there are fewer search intervals. That's good. But this O of 1 error term will go up. Right? If we allow this to be bigger, then we won't be able to approximate f of x as well by f of p0. Okay. Well, what I'm going to do is pick some particular parameters. So I'm going to basically I'm going to take a larger value of b and a larger value of delta, so that my interval has now gotten bigger. So now instead of p0 over n to the 1 third, I have p0 over n to the 1/5. So I've got a bigger search interval, but I'm allowing this error term to grow. It's no longer O of 1, it's O of n to the 1/5. And the reason I chose 1/5 is because this is the point where this error is going to match this denominator. That just turns out to be the solution to the optimization problem. Okay, so the search interval width has increased. The number of search intervals has decreased. That's good. But what's bad is the error term has gone up. And so now if you just tried to do Lehmann's idea, then it's not really going to help, right? Because you need to test a lot more candidates, right? I mean, you compute f of p0, but now instead of just O of 1 candidates to test, you've got O of n to the 1/5 candidates to test. And if you did all of them one by one, you'd end up overall with a complexity of n to the 2/5, which is awful. It's not quite as bad as trial division, but it's certainly worse than all the other algorithms we've been discussing. But that's not what we're going to do. And this really was Hittmeir's idea, is you can search all the intervals at the same time. Actually, I guess this is the difference between Hittmeir's algorithm and my simplification. In my simplification, we really do all the intervals at the same time. He wasn't quite able to do all of them at the same time. He had to sort of split them up into different types. And I found a way to do them all at the same time. So how does this work? So here again is the estimate we had on the previous slide. And I'm going to write this as follows. I'm going to bring this is a known constant, an over p0 plus b p0. Let's just call that u. I'll just round it to an integer and call it u. Bring that over to the other side. And so we have an over p plus bp minus this u is equal to some unknown k, where k is pretty small. It's at most n to the 1/5. And now this is the crucial thing. I'm going to take my alpha of large multiplicative order, and I'm going to raise alpha to the power of both sides. And then something magical happens. What happens is on the left, we can get rid of the p's, the unknown p in the exponent using Fermat's little theorem. Right, alpha to the p is just alpha. Alpha to the n over p is just alpha to the n. So on the left-hand side, we have this expression which doesn't depend on the unknown p anymore. In fact, we know everything on this side, right? We know alpha, we know n, we know a and b because they were chosen for each individual, each interval, and we know u, right? U is again just a function of all these known things. And on the right-hand side, well, we don't know k, but we know a bound for k. So what happens is on the left, you've got one possible value for each search interval, and on the right, you have one possible value for each little step within that search interval. Sorry, that's not what I meant to say. Not within the search interval. For one step for each of the unknown values of k. So we've got n to the 1/5 values on the left and n to the 1/5 values on the right, and we're looking for a collision modulo p between these two sets. And then what we do is we just throw Pollard's machinery using the polynomial multiplication and evaluation and so on to find that collision. And the complexity ends up being only about n to the 1/5. So it's really the same idea, but just applied to, it's basically Pollard's idea, but applied to sets coming out of Lehmann's algorithm with the parameters adjusted a bit. So it really is very much just a combination of those two algorithms. Okay, so I'll just make a few more comments about this algorithm. So the algorithm I've showed you today is a simplified version of the one in the various papers that we've written. What it will give you n to the 1/5 times some power of log n. You can work out what the power of log n is. But there are various tricks available to optimize that power of log n, mainly to do with finding more structure in things like the baby steps and using geometric progressions and so on. So nothing very spectacular, but you can save a bit of a power of log n there. And then I mentioned that there's also this log n improvement, and where this comes from is sieving on small primes. So you use the fact that you know right off the bat that p is not going to be even. Right, that already cuts out half the candidates, and then p can't be divisible by 3, and so on. And so you do this for a number of primes, and you're able to get a saving coming from Merton's theorems. So that gives you a little saving there. And finally, one question which some people may be wondering about, and I thought an awful lot about this earlier this year. I spent months of my life thinking about this question. Is can you do any better by trying to increase the degree of the polynomial the way that Coppersmiths does. It's a very tempting idea. When I first thought of this idea, I was like, yes, I'm going to beat n to the 1/5. I was so certain it was going to work. And look, maybe it does, but I couldn't get it to work. Hopefully someone else can figure out how to do it. But what actually seems to happen is that, so if you start with Lehmann's algorithm and then you start increasing the polynomial degree, the complexity improves. But if you start with this n to the 1/5 algorithm and start increasing the polynomial degree, the complexity actually gets worse. And in the limit, it ends up being n to the 1/4, just like Coppersmith's algorithm, except that you end up with an algorithm that's just as slow, but also uses a lot more memory than Coppersmith. So you really lose in every possible way. So I feel like at some level, I don't understand why this is happening. And it's just what comes out of when you try to optimize things. It's something to do with the fact that the higher degree terms move too quickly, but I can't really be any more precise than that. It's a bit strange. Anyway, hopefully someone will figure out what to do, and then maybe we can get n to the 1/6 or sub-exponential or something like that. All right, that's all I have to say. Thank you very much.
Thanks very much, David.
Yeah, thanks, David. That was great talk. I just had one question about the guess in Lehmann's algorithm. So you have to guess a number first. And is there how do you guess this number? And is there some optimization possible there?
Right, so you don't actually have to guess. What you do is, the way this is organized is that, where is this slide? Here we go. So the way this works is that if you do decide to guess, then, and if your guess is correct, then what Lehmann is showing is that you will find the prime. But if the guess is wrong, I mean, you can still run the algorithm and you just won't find anything. It just, like, nothing will happen. It'll just finish the computation. You'll go, oh, nothing happened. So then what you do is you just try every possible guess. That's where the n to the 1/3 is coming from. There are sort of n to the 1/3 possible guesses that you need to try. Right. But if you did happen to know that, the first whatever number of digits of your factor were given by some guess, for example, maybe you have some cryptographic system and there's some leakage from the device, and you're able to get a few of the initial bits. That would be an example where you have some information that you might be able to use as a guess. Right. Yeah, I think maybe the word guess is a bit misleading, because maybe that obscured the structure of the algorithm a bit. Yeah, I hope that clears it up.
Yeah, it did clarify my question. Thank you. Yeah.
I'm wondering how practical is that algorithm. For example, yeah, well, of course, it cannot beat a number field sieve, but let's say if you're talking about Pollard's law or Brand's method, they are quite effective for numbers, I don't know, from 20 digits to 30 or something. Well, will this method be faster, or?
No way. Look, I did try implementing it, right? Just as a sanity check, I have implemented at least one version of this algorithm over the last year or so. And the thing is, I know the implementation must have been pretty good, because really it spends all its time multiplying huge integers, and you don't get much choice about how big those integers are, and it'll basically spend all its time in a library like GMP multiplying huge integers. So my implementation was probably reasonably close to optimal, and it was horrifically slow. Okay, you would take a big number and you'd run it, and it would be grinding away there for some minutes, and then finally it would spit out the answer, and then you ask Sage or whatever to factor the number, and it's instant, right? So there's a lot of things going on. There are some bad powers of log n. There are some bad constant factors. Well, the constant factors aren't that bad, but they're not great. One big problem is this algorithm uses a lot of memory, right? It's n to the 1/5 memory as well as time, which is just horrendous. And these other algorithms you're talking about, I mean, they are just brutally fast and use no memory and have very good constants. And I mean, I'm certainly not an expert on that class of factoring algorithm, but there's no way that an algorithm like this can hope to compete with any of those.
What if you? Sorry, what if you're trying to find like smallish factor? Will it increase? Will it be faster?
I don't think so. I think that the heuristic algorithms that we have, I mean, maybe Richard has something to say about this, but the other heuristic algorithms we have are going to be way faster. I mean, one interesting feature actually, since you mentioned finding small factors, if you're trying to find a relatively small factor of a large number, then this algorithm doesn't really get any speed up from knowing that it's small. It's quite surprising because Pollard's algorithm does. Pollard's algorithm, if you're looking for, if you have a bound of say b, then you can find that factor in something like square root of b time using Pollard or Strassen, or I think Pollard Row maybe also does that, which is really great when p is small. But this algorithm, you actually don't get that. You still get n to the 1/5. It's very strange.
Okay, thank you.
Yeah, David, if I can just comment,
Yeah.
Pollard Row or Lemche's elliptic curve algorithm, the time bound or expected time bound depends on the size of the factor, not the size of the numbers. Now they're going to win if you have small prime factors.
Yeah.
Look, when you approximate p naught squared over n, you assume the worst case, right? Typically, you can put another logarithm in the denominator of your approximation, because partial quotients, they grow slightly, right? Will it give, say, for a typical case, can you get a slightly better bound? It won't beat 1/5, but it may shave you some logs off. I don't know how to make a rigorous statement, but kind of heuristically expect that for randomly chosen n, you will put log b in the denominator of the approximation.
You mean an extra log b in this denominator here?
Yes.
Okay, I didn't know that. You're saying that works for most values of zeta, but not all values of zeta?
Well, it's known for almost all real numbers, how partial quotients behave. They grow logarithmically with the index. For rational numbers, it's a trickier thing, but heuristically you should expect this to be a little bit better.
But I'm not sure that it will work for this particular case, because, well, we know that they exist somewhere, that there exists such a good approximation, but it's not what we find, right? We find one precise approximation, and that one may not have logarithm there.
But it is true that almost all partial quotients, they grow like logarithmically with their number.
A maximum of them, yes, but not all.
Okay, yeah, maybe I'm wrong.
Well, I mean, something like that might be good enough because you're doing a search, right? And if you can cover most of the cases with a faster algorithm, and then there's not so many cases left to check, you might be able to check them some other way. So I'd be interested to have some reference to whatever this phenomenon is you're talking about. I'm not familiar with that.
Well, I have one. I've written down slide 29 ... So I hope that I can figure out what that means. If you could go to slide 29, please. Right. Now, is it just me, or is that number at the bottom something like pi times something?
Must be just you, Tim.